right, here we are with section 4.1 to 4.2. We've been looking at axial loads, and we are now kind of combining everything. So remember, with axial loads, we have that normal stress is that internal normal force divided by cross-sectional area. We have that in the elastic region, stress equals E times strain. We have strain equals length final minus length initial over length initial, which is also delta over initial. We also looked at, in our lecture we just had, that we can pop this over into the stress, and we can pop this over into the strain, and we can come up with our new equation, where delta equals PL over AE. Again, this is valid in the elastic region. Okay, we have to be inelastic. So we've got to be constantly checking our stress, because we need to make sure the stress that we're working with is less than the yield stress that we would find from a chart. Okay, so here is an assembly. It consists of two 10 millimeter diameter red brass copper rods, A, B, and C, D, and a 15 millimeter diameter 304 stainless steel rod, EF, and a rigid bar, G. So the rigid bar is important because we're going to have rigid body rotation or rigid body translation. We are not going to consider any deformation here if this were to actually bend like a beam, because it is a beam, right? It's a beam that's being pushed on, then it would add to that deformation. So we're just going to, it's a perfectly rigid body rotation, rigid body translation. Determine the horizontal displacement of end F of rod EF. Okay, so as I pull here on this hook, I can see that's tension. We're going to have a change in this distance here, the change in this length. We're going to be pulling in this direction. We're also pushing, so we're going to have to look at those values. So these two members could either be in tension or compression. So when I'm looking at the overall, when I'm looking at the change in length of F with respect to, we're just going to call that AC, then it's going to come from the change in length from E to F plus the change in length from, okay, A to B. And I want you to stop and think, why am I not also saying plus the change in length of C to D? Okay, why would I not also want to add that on there? Okay, I have to think about, this is a linear system, and AB and CD are going to have that same change in length. Okay, so I don't need to count both of them because they're not additive. They are happening at the same time. Okay, and it's symmetric, so they should be the same amount of change in length. So I just need the change in length of one, and then the change in length of this to find the total change in length. So when I'm looking up here, this is made of red brass, and it also tells me what the diameter. So the diameter of both of these is 0.01 meters. And if I am looking at red brass, then I am looking at a modulus of elasticity of 25 times 10 to the negative, that is not at all what it's going to be. It is going to be 101 times 10 to the 9th, because it was in gigapascals, which is 10 to the 9th, 101 10 to the 9th, and I'm going to note that is now in just a Pascal, which is a Newton per meter squared. So I'm making sure everything is consistent in the units that we're working with, and these have an original length of 0.3 meters. Okay, when I'm looking at this bar, E to F, the diameter was given as 15 millimeters, so 0.015 meters. And the modulus of elasticity for this material is 193 gigapascals, which is times 10 to the 9th pascals, which we know is a Newton per meter squared. So my units are all working out. And we have an original length of 0.450 meters. So I have everything that I need. When I'm looking at change in length, okay, change in length is P, so I need to find the internal force, L That's given. A, that comes from my diameter. E is given. So now that we have this done, we're going to draw free body diagrams. Remember, we always start with equilibrium free body diagrams. And I'm going to start here on the right. So I'm going to cut and find the internal. Then I'm going to come across and I'm going to cut and I'm going to find the internals. So we have to use everything to the right or everything to the left. So if I look to the left, I'd have to include my reactions at the wall, which is an extra step. If I look to the right, it's a pretty short little specimen here. So I have 4P, and P is 5 kilonewtons, so I have 20 kilonewtons. Pulling to the right, and I have an internal normal force, a normal force from that's in FE, okay? Remember, we could also find shear and bending moment and torsion, but the only load we have right now is axial, so I can sum my forces in the x direction equals 0, and I can get the negative normal from F to E plus 20 kilonewtons equals 0. So the normal force in F to E is 20 times 10 to the third newtons. Remember, I'm putting everything in newtons. And now I'm going to come across and I'm going to cut. So I have another free body diagram. So I still have that 20 kilonewtons pulling to the right. And I have this rigid bar, and I have now cut, okay, I've cut in here. So I have a force from B to A, and I have a force from D to C. And I also have 5 kilonewtons pushing and 5 kilonewtons pushing. And because of symmetry, I know that these have to be equal. So now let's set up our equilibrium. Summing forces equals 0. So I'm going to have, we're going to just say 2 times because we know that they're the same, and I just need to find the deformation of 1. But anyway, so we have 2 times FBA because we know they're the same. Okay, negative minus 5 plus 20 equals 0. So we have 2 force BA equals negative 20 plus 10, which is negative 10. So I know that we're in compression. Our delta is going to be compression. So that force BA equals negative 10 divided by 2, which is negative 5 times 10 to the third newtons. And I can leave it as a negative 5, or I can note that it's in compression. But it's super important to understand, okay, if it's positive, then we are getting a positive change in length. If it's negative, we are actually getting shorter. And did I do my math correct? Plus 20. And if I have 20 going this way, then I'm going to have 5 kilonewtons going that way, and then the 2, oh well, this is negative over here, and I totally took it away. So look at that, my math is awful. My math is awful because I took these over, but then this would have stayed a negative, so then I have to get rid of my negatives, okay? Terrible, terrible. It's a huge difference because if it had been negative, they would have gotten shorter, but it is in tension, so they are going to be getting longer. Okay. So I now know this part, my ends, I know that internal force, I know my lengths, I know my areas, I know my E's, and I calculate my delta. So what should I do? If I have a stress strain curve, what should I do? I need to say, are we in the elastic region? Are we in the elastic region? Is the stress in FE, is it less than the yield stress of my material? And I know that stress in FE equals that normal force, 20 times 10 to the third newtons, divided by cross-sectional area, pi over 4.015 meters squared. And when I calculate this out, I finally got batteries back for my calculator. I'm going to have 20 times e to the third, 20 times e to the third divided by pi as a number, 4 divided by 0.015 times, 0.015 times, divided by, and I get this ginormous number. So I'm going to have to move this over. 1, 2, 3, 4, 5, 6, and I get 113, okay, megapascals. And so I would need to check, is this less than the yield stress for the material? Because if it's not, I cannot use this equation. I would need to go to a stress strain curve to actually calculate that strain. But because we don't have those for these, the book doesn't provide those, we're just going to assume at this point that everything is in the elastic region. So as such, I know that the change in length from F with respect to A equals delta EF plus delta AB. And again, I don't need to do both AB and CD because they are moving the same amount. So that's going to be the normal force, okay? The normal force in EF, the length of EF, the area of EF, the E of EF, plus the normal of AB, the length of AB, the E of AB, the area of AB, and I can just start plugging in numbers now. So the change in length from F with respect to A equals, that normal force was 20 times 10 to the third newtons. PL, look, I have everything organized, 0.45 meters divided by area, pi over 4, 0.015 squared, and then I have properties, 193 times 10 to the 9th Pascal. Okay, plus, again, we found it was in tension. I boogered up on the math, but I quickly caught it. 5 times 10 to the third. Okay, its length, again, I have everything up here in my chart, kind of started. Everything is here. Okay, my area, pi over 4, d squared, 0.01 squared. And then their material property was 101 times 10 to the 9th. And now that's easy peasy, easy peasy. I can use my calculator to calculate all of this out, okay, to calculate all of this out, and I'm going to get 0.453 millimeters. So it was actually a much smaller number because look, our units are all in meters, okay, our units are all in meters, and then I divided through by 1,000, so I know that that change in length of the total system is 0.453 millimeters.